We are going to continue with a uniformly charged sphere. So that's the second problem that I'm going to solve. So that's one of the simplest. Basically, we have a sphere with radius r and it has a total charge q, but this charge is distributed uniformly over the volume of the sphere. So there is a volume distribution of charge. So let's just look at this picture in here. So probably that kind of gives you an idea about what the shape is. So the shape is sphere and the inside is filled as well, and somehow the charge is distributed uniformly. Okay, so we would like to find the electric field produced both inside and outside. In any case, we need to quantify the distribution of the charge. So for that, we use the volume charge density. Volume charge density. All right. So in all of these cases, we are going to use the Greek letter rho to describe this. So that's basically charge divided by the volume. Okay. And in this case, this is given as, since the charge is given as q, the volume of sphere with radius r is 4 pi over 3 r cube. So therefore, this is our charge density, r cube. Okay, so let me also write this thing down. So this is the Greek letter rho. This is the small lowercase Greek letter. The capital rho is basically looks like p. So as a result, we don't use it often. But for representing the volume charge densities, we usually use this symbol. Okay, so then let's solve the problem. So I'm going to start with the electric field outside. So I'm going to consider a point in here with a radial distance r from the center, and we would like to find the electric field in here. All right. For this purpose, we just draw a Gaussian surface, which is sphere. It's a sphere with radius little r. So it's passing from this point, and so we use Gauss law to express to relate the flux to the enclosed charge. Right. So let me show the dot product clearly. Enclosed charge divided by epsilon 0. So this is the Gauss law. So first we can find the enclosed charge easily in here. It's the total charge. So as a result, I don't have to deal with the densities and things like that. I already know what the total charge is Q. So therefore, this is Q divided by epsilon 0. And on the left-hand side, this calculation is the same, but let me do the calculation in the same way. So in the first step, we just express the dot product as a product of the components, the radial components of these vectors. Take the radial component of the electric field outside. Replace this thing with the surface area of the Gaussian surface. And so as a result, we have this expression. And from here, we find the electric field outside as 1 over 4 pi epsilon 0 q divided by r squared. It's the Coulomb's law expression. For an outside point, it doesn't matter whether the charge is distributed over the volume of a sphere or the surface of a shell or whatever. So you can actually imagine that all of this charge is collected, concentrated at the center, and that point charge at the center would produce the same electric field as this one. So the size of the sphere and things like that do not enter into that expression in here. All right, that's always good to know, but we need to do the calculation like that in any case. All right, so then let's go what happens inside. So in that case, well, that case is still the same. So we just draw the Gaussian surface. It has to pass from the point in question, and it has the same center as the center of the symmetry of the problem. And then for that surface, I write the Gauss law. Yeah, let's just quickly write this thing down. I always compute the right-hand side first, but let me quickly do the left-hand side first. So Dot product is converted into this. E is odd, and then this is E times 4 pi r squared. So this step is the same in all of these problems. The right-hand side changes in here. So in that case, part of the charge autosphere is outside. It's not enclosed. So all of the enclosed charge is in here, in that shaded region that I'm shading right now. Okay, so as a result, all of the charge is in here. So let me call this as, well, it's called as Q enclosed. That's basically density multiplied with the volume enclosed. It's the volume of the Gaussian surface, volume inside the Gaussian surface. So that's 4 pi over 3 little r cubed. Little r is the radius of the Gaussian surface. So therefore, this is 1 over epsilon 0 rho 4 pi over 3 r cubed. Right? Let's just compute it like that. So in any case, 4 pi cancels with that 4 pi. So the electric field is then rho divided by 3 epsilon 0 times r. So that's the expression, but it is customary to express everything in terms of the given. So instead of this, let's just use this expression. The charge density was, I just computed somewhere else. The charge density was 3q divided by 4 pi r cubed. And I'm just going to insert this value in here. And so therefore, the electric field has a magnitude which is given as 1 over 4 pi epsilon 0 q divided by r cubed times r squared. Okay, so therefore that's the value of the sorry about that. I made some kind of a mistake in here. So that's not r squared r. All right, so that's the correct expression. Okay, so then let's just write down this. So sometimes I'm going to write this thing down like that. So by using the mathematician's definition symbol. So inside the electric field is 1 over 4 pi epsilon 0 total charge divided by the radius q times little r. So that's let's say 4r is less than the radius of the charge sphere, and outside is 1 over 4 pi epsilon 0 q divided by r squared. So that's 4r bigger than r. Okay, so it is quite easy to see that these two electric field expressions match at the point at the radius of the sphere, right? So as a result, if I draw this curve, so let me use a thick color for that. In any case, I'm going to get a linear expression inside and 1 over r squared expression outside. Let me go back and mark this point. So that's at the radius of the sphere. So at the radius of the sphere, both the electric field inside and the electric field outside has the same value. So if you want to be mathematically precise, you can use an equality sign in here. So both expressions are going to give the correct electric field in here. In any case, one of the nice features in here is this, that the electric field at the center is 0. Right? So let's just note this. Note E equals 0 when R equals 0. This is actually an essential, it's something that you would expect, right? Because that's the center of symmetry. So let's just go back to the original picture in here. So we have some kind of a charge distribution in here. It is spherically symmetric. I know that at all points the electric field is pointing, if this is a positive charge distribution, the electric field is pointing radially outward. And so as a result, you can kind of see that because of the symmetry of the problem, the electric field at the exact center should be exactly equal to 0, because only in that case, when you rotate the charge distribution, the electric field at the center doesn't change. So as a result, this is a welcome feature. That's one of the checks that you can always make, that whether the electric field at the center is in spherically symmetric problems, check that the electric field is at the center is indeed 0. Okay. So I think there's nothing else that we can say about this problem. So let's stop in here.